Alright, in this last part of lecture 3, we'll look at the example in chapter 1, page 8. That's the example again. That's the example which again involves cubic equation like this. X cubed take 6x plus 4 equals 0. At this time, we're given that one of the roots is 2. So x equal 2 is a solution. So when you know one of the roots, you do what is called division of the, because when you know that the x equal 2 is the root of a polynomial, you know that the factor x take 2, must be present in the factorization of this polynomial. And you're looking for this factorization like so. You take your polynomial and you do a division as if you divide numbers. So you take this polynomial x cubed takes 6x plus 4 and you try to divide it by x take 2 like so. First you take x squared here, because if you multiply x squared across this polynomial, that's the result of that will be x squared times x squared times x cubed, negative 2 times x squared, negative 2x squared. And then you subtract this result of this multiplication from your original polynomial. The result of this subtraction, clearly x cubed is gone. This x squared is not present here, so the difference will give you something like this: 2x squared for this, negative 6x squared from the top, and plus 4 is here. Now you look at this latest polynomial and you do the same thing you did with your initial polynomial. You just try to guess an extra factor, which if you multiply this extra factor by your x take 2, you will cancel out this highest power of x here. Obviously this factor is 2x. If you multiply this 2x with x take 2, that's what you will get. 2x squared take 4x. If you subtract, 2x squared now gone. Here, if you subtract 4x, negative 4x in fact, from negative 4x, the result will be negative 2x, and 4, I have to copy 4, just simply like so. Well, again, we repeat the same step. We try to guess something here, which if multiplied by x take 2 will cancel this negative 2x, and this guessing again very simple, it's just negative 2. If you take negative 2 times x take 2, that's the result. Happens to be identical, and that's not a coincidence, of course. When you subtract, you end up with the remainder 0. This is not a coincidence, of course, because you knew up front that that number 2 is a solution. So if you call now this polynomial p of x, I don't want to copy it again, actually I forgot this line. If you call this polynomial p of x, then we just realized that my polynomial p of x, here it is, it factorizes like this: x take 2, and then goes my quotient we have just found in our procedure. So when you go after roots of your initial polynomial, like so, obviously you have one root x equal 2, that's the one which was given to us up front. And when you go for the second roots, you're looking now at quadratic equation, and you know the formulae for the solutions of such quadratic equation. In fact, your b coefficient here is even integer, so you can use half formula for that. So you got your two other roots, x2 and x3, and you go negative b half, negative this b half, then goes your root of the discriminant, and 1 at the bottom. You can do the arithmetic here, and that would be a result of this arithmetic. Now, this is it. That's how you solve this question. However, I want to make some extra comments in relation to this division procedure. Big one. There is another one which, in my opinion, is shorter. And if I start again with the same polynomial, like so, and I'm after factorization. I know in advance that x take 2 is a root, so this factor must be present there. So my job is to identify this quotient again, but now by a slightly different procedure. So what I do is this: I take my first highest coefficient here. I know in advance that x take 2 must be present as a factor. So what I will do, I will manufacture this. I will deliberately manufacture this factor. Look at this. I'll put next to this x cubed negative 2x squared. The reason I put this negative 2x squared here is that because these two elements together, they factor like this. They have a common factor x squared, and if you take it out, the rest will be the bracket x take 2. That's the bracket which we have to factor out. Now, time has come to do something with this negative 2x squared, because this is something which is not present here, so this equal sign is not legitimate. What I will do, I'll just cancel it out. Now, obviously, this is in combination, it's just 0. So basically, I haven't changed much. Just the whole expression, just x cubed, still just one single term from the upper polynomial. Now, what I will do next, I'll copy my. No, I won't copy that. Now I look at this plus 2x squared. So I'll again intentionally just put next to it negative 4x. Why? Because these two together, again, they produce the bracket I'm after, the bracket 2x times x, the bracket x take 2. Because these two have a common factor 2x, and that's how it factors. Well, again, negative 4x isn't something which is present in my original polynomial. In fact, negative 6x is present. So in order to make this 6x, I will add up another negative 2x. These two terms combined, they produce negative 6x. So far, all the terms I have written, they together, they just correspond to these two terms of my original polynomial. Now finally, I copy my last term of the original polynomial, and these terms happen just to produce another bracket x take 2, because they have a common factor negative 2. And we're almost done. Here's my bracket x take 2, here's my bracket x take 2, here's my bracket x take 2. I can now factor this bracket out. So here's my bracket, and now I combine all what remains: x squared, 2x, negative 2, x squared, 2x, negative 2. That's my quotient we found earlier with the other method.